Hey everybody, and welcome back to another AI.Code.Cast deep dive. Today we're going to be talking about reversing a 32-bit signed integer.
Ooh.
Yeah. Which sounds pretty straightforward, right?
Uh-huh.
I mean, we all know what integers are. We all know what reversing something means.
Yeah, you just like flip it around.
But there's always some little gotchas in these classic coding problems, and this one in particular can really trip people up when it comes to integer overflow.
Integer overflow. Yeah, that's the one that gets everybody.
Yeah. So to really set the stage here, we're given a 32-bit signed integer.
Right, so it can be positive or negative.
Exactly. And our goal, our mission, is to reverse the digits of that integer.
So like 123 would become 321?
Exactly. And negative 456 would become negative 654.
Right.
But the kicker, the real challenge here is that the reverse number still has to fit within the bounds of a 32-bit integer.
Yeah, if it's too big or too small, it's like
overflow,
and then the answer is just 0.
Yeah, it's like we're working with a limited set of building blocks, right?
Yeah.
We can rearrange them, but we can't like create any new ones or the whole structure collapses.
That's a really good way to put it.
So how do we even approach this? Like what's a good starting point for thinking about this problem? I mean, I guess the most like intuitive way would be to just treat the number like a string, right?
Yeah. I think a lot of people would probably go that route first. Like you convert the integer to a string, you reverse the string, and then you convert it back to an integer.
Yeah. I mean, that makes sense, especially if you're comfortable with like string manipulation.
Yeah, it's kind of like taking it apart, flipping the pieces, and putting it back together.
Yeah, and it seems pretty straightforward, but I have a feeling there's like a more elegant way to do this.
Oh yeah, there definitely is.
What if we like stay in the world of numbers and use math to directly reverse the digits?
Ooh, now you're talking like a seasoned coder.
Okay, give me a hint here. Like what kind of math are we talking about?
Well, remember how we use that modulo operator to figure out if a number was even or odd?
Right. That's that percentage sign in most languages, right?
Exactly. And it can also help us isolate individual digits of a number.
Oh, interesting. So like you take the modulo of a number by 10, you get the remainder after dividing by 10, which is always the last digit.
Exactly.
So 123 modulo 10 would give us 3.
You got it. And once you have that last digit, how could you shift it to the beginning of a new reverse number? Think about the place values units, tens, hundreds.
Okay, so if I multiply the reverse number by 10 and then add that extracted digit, I'd essentially be like pushing that digit to the next place value.
You're getting it.
So if my reverse number is initially 0 and I add 3, it becomes 3, then multiplying by 10 gives me 30 ready for the next digit.
Perfect. And to keep things moving, you would also need to chop off that last digit from the original number. What operation could you use for that?
Integer division.
Ooh.
If I divide 123 by 10, I get 12, effectively removing the 3.
You got it.
Then I can just repeat the process. Extract the last digit with modulo, add it to the reverse number after multiplying by 10, and chop off the last digit from the original number using division.
You've just described the core logic of the mathematical approach.
Nice.
But before you get too excited, remember that overflow issue we talked about?
Oh, right. Yeah, it's not enough to just reverse the digits we have to make sure that our result doesn't, like, exceed the limits of a 32-bit integer.
Exactly. And that's where things can get really tricky. Instead of checking for overflow after we've built the entire reverse number, what if we could check for potential overflow during each step of the process?
Okay. Yeah, that sounds like a much safer approach. But how do we even know if adding another digit is going to push us over the edge?
Here's another hint. Instead of comparing the reverse number directly against the maximum integer value, think about what happens if the reverse number is already greater than the maximum value divided by 10.
Okay, so let me wrap my head around this. If the reverse number is already bigger than that threshold, multiplying it by 10 will definitely cause it to overflow, even before adding the next digit.
Exactly.
Okay, I'm starting to see it.
And we can do a similar check for negative numbers using the minimum integer value divided by 10.
So this little trick, this lets us like integrate the overflow check directly into our loop.
Exactly.
So we never create an invalid result.
You got it.
Wow, that's pretty slick.
Yeah.
We've gone from like this basic string reversal approach to like a more sophisticated mathematical solution with a built-in safety net.
Yeah, and that's just the beginning. Now that we've laid out the groundwork, let's dive deeper into each approach, compare their pros and cons, and really solidify your understanding.
Stay tuned for part 2.
Welcome back to AI.Code.Cast, ready to get our hands a little more code dirty.
Let's do it.
All right, so we've got the blueprint for reversing those integers. Now let's actually see how these approaches play out in like practice. When we start thinking
Mhm.
about pseudocode.
Yeah. It's one thing to talk about the concepts, but actually seeing them in like pseudocode form is where I feel like those real aha moments happen.
Totally.
Let's start with that string reversal method, since that seems to be like the most intuitive one, at least for me.
Yeah, definitely. So imagine we're writing this function, right? First, we take our input integer and we've got to convert it into a string.
Okay.
Most languages have a handy function for this, something like toString.
Right. So our integer like 123 would become the string 123.
Exactly, easy enough. And then we need to flip that string around.
Okay.
There are a bunch of ways to do this, but what's a common approach?
Yeah, I mean, a lot of languages have like built-in functions or libraries
Mm,
specifically for reversing strings.
right.
You might see something like a reverse string function or even use some special slicing techniques depending on the language.
Yeah, Python slicing is pretty slick for this.
It is, yeah.
Yeah,
But the point is we end up with 321 as our reverse string,
exactly.
and then we just got to turn that back into an integer.
Exactly. We use a function like parseInt to convert that reverse string back to an integer, and bam, we've got our reversed integer.
Boom, done. Simple, clean, easy to understand. Even for folks who aren't necessarily like math whizzes.
Exactly.
But I know you hinted earlier that this might not be the most like efficient way to go, especially when we start dealing with like really large numbers.
Yeah, well, think about what's actually happening under the hood. Converting between integers and strings, it involves a lot of like behind the scenes work for the computer.
Oh, really?
Yeah, it has to go through each character, interpret it, and then rebuild the data in a different format.
So even though it seems really straightforward to us, it's actually like quite a heavy lift for the computer.
Yeah, and this overhead gets even worse as the number gets bigger. More digits means more characters to process, and it can really slow things down,
Yeah.
especially if you're doing this operation a lot like in a tight loop.
Right. And I know like some interviewers, they really aren't thrilled if you rely too heavily on these like built-in functions.
Oh, yeah, they want to see if you can handle the logic yourself.
Exactly. So let's dive into that elegant mathematical solution that we were talking about.
Okay, let's break it down.
Okay.
Imagine we have a loop that continues as long as our original number isn't 0.
Okay.
Inside this loop, we're going to be performing 3 key steps.
Okay.
First, we isolate the last digit using the modulo operator. That's our trusty %10 trick.
So we're essentially like popping that last digit off the number, like taking the top plate off a
I
stack.
love that analogy.
Okay.
Second, we take our reversed number, which starts at 0, and we multiply it by 10.
Mm-hmm.
This shifts all of its existing digits one place value higher, making room for the new digit.
So it's like we're making space for that new plate at the bottom of the stack.
Exactly.
Nice.
Then we add the pop digit to our reverse number, effectively pushing it onto the stack.
Uh-huh.
And finally, we use integer division, that /10, to chop off the last digit from the original number, preparing it for the next iteration of the loop.
Okay, I'm seeing the pattern here. It's like a little Bidget assembly line, pop shift, push repeat. But we can't forget about that overflow check. Where does that fit into all of this?
This is where the real elegance comes in. Remember that trick with int max divided by 10?
Yeah.
Before we shift our reverse number by multiplying by 10, we check if it's already bigger than this threshold.
Right, because if it is, we know multiplying it again is going to make it overflow. So we just immediately return 0 and avoid disaster.
Exactly. And we do a similar check with int and min divided by 10 for negative numbers. Yeah. This way, we're constantly safeguarding against overflow without having to wait until the very end.
Man, I am really appreciating how efficient this solution is.
Right.
We're staying in the world of numbers, we're minimizing those costly conversions, and we're proactively addressing that whole overflow issue.
It's a beautiful example of how understanding those fundamental mathematical operations can lead to elegant and efficient solutions.
Absolutely. But like any approach, it's got to have its trade-offs, right?
Yeah.
What do you think might be like a drawback to this approach?
Well, for someone just starting out with algorithms, the logic behind the modulo and the division steps might feel a little less intuitive than just flipping a string around.
Right.
It does require a deeper understanding of how numbers work.
So it's kind of like choosing between a power tool and a handcrafted instrument. The power tool is quick and easy, but it might lack that finesse, while the handcrafted instrument takes more skill to use, but it can produce some incredible results.
Ooh, I love that analogy.
Yeah.
It highlights that there's no single best solution. It all depends on the context.
Right.
So now that we've got a really solid grasp of both of these approaches, let's shift gears a little bit and explore some of those real-world scenarios where integer reversal, or at least the concepts behind it, might actually come into play.
Okay, I'm intrigued. And we are back for the thrilling conclusion of our integer reversing adventure here on AI.Code.Cast.
That's right. We've covered the why, the how, and even the watch out for that overflow.
Now it's time to put all of that knowledge to the test.
And see if you, dear listener, can apply what you've learned.
Okay, so first challenge. Imagine you're working on a security system that uses unique numerical codes.
Okay.
And to make it harder to crack, you want to reverse those codes before you store them.
Ooh, good idea.
Which approach would you choose and why?
That's a great example.
Mhm.
In this case, security and efficiency are really important. So that string reversal method, while it's simple, it might not be the best choice because the string conversions could potentially create like vulnerabilities
Right.
or slow down the system, especially if you're dealing with a lot of codes like in real time.
You don't want any lag when someone's trying to disarm their security system.
Exactly. So the mathematical approach seems like a better fit here.
Yeah, I think so too.
Yeah.
It's faster, it's more secure, and it really demonstrates that deeper understanding of how to manipulate numbers directly.
Plus, that built-in overflow check adds an extra layer of protection against potential errors or attacks.
Okay, so challenge number 2. You are designing a data compression algorithm
Ooh.
for sending messages over a limited bandwidth connection. And you notice that certain numbers appear very frequently.
Right.
Could our integer reversal techniques help here?
Absolutely. This is where understanding that logic behind those modulo and division operations really shines. Think about it. If you can efficiently isolate those individual digits, you can start playing with how those digits are actually represented.
So instead of sending the entire number, maybe we could send like a shorter code that represents the pattern of its digits.
Exactly. You're starting to think like a data compression expert.
Wow.
This is actually how techniques like Huffman coding work. They leverage the frequency of these data patterns to create more efficient representations, which is essential for saving bandwidth and speeding up transmission.
Wow, who knew that reversing integers could lead to like all of these clever solutions? It's like that old saying, give a coder an integer and they'll reverse it for a day. Teach a coder how to reverse an integer and they'll solve all sorts of problems.
Couldn't have said it better myself.
Okay.
The key takeaway here is that the value of learning these seemingly basic algorithms goes way beyond just the specific problem that they solve. Yeah.
It's about developing that flexible problem-solving mindset that you can apply to all sorts of challenges.
Absolutely. Well, folks, that wraps up our deep dive into reversing 32-bit signed integers.
Sad to see it go.
We hope you've not only learned how to tackle this specific problem, but also gain a deeper appreciation for the power of algorithmic thinking.
Remember, coding isn't just about memorizing syntax or libraries. It's about understanding that underlying logic and using it to create elegant, efficient, and effective solutions. Keep experimenting, keep learning, and keep those coding brains buzzing.
From all of us here at AI.Code.Cast, thanks for joining us on this deep dive. Until next time, happy coding.